Hey kids, it's great to see you. My name's Jeff Galvin. I'm the CEO of American Gene Technologies. And actually my previous career before getting into biopharmaceuticals, biotech, drug development, was in software and computers and internet and apps and IT. So I know exactly what you're doing, and I think you're in an amazing field. I think any knowledge of how to work with computers is going to be valuable. It's been valuable for the last 60 years, and it's going to be incredibly valuable for the next 60 years as computers start to do more and more to make our life easier. Well, now I'm into a new type of programming. What I do is I program DNA. So you may not be aware of this, but software, the kind of things that you're doing, extends past digital computers. It isn't just for the computer on your desk or the phone in your pocket. It turns out that the concepts that you're learning can actually extend into biology, can extend into drug development, can extend into curing diseases. And what I'm going to do is explain to you how that is, and hopefully it might inspire some of you to keep going in this and go on and apply your science, technology, engineering, and math skills to finding cures for diseases. Maybe one of you will even go on and cure COVID. You never know. So, what do I mean by programming DNA? Well, you may not be aware of this, but your cell is like a teeny organic computer. You know your body is made up of trillions of cells, and these cells collaborate with each other to make you. There are nerve cells in your brain that process thoughts. There are stomach cells that put out acid to dissolve your food. You have light-sensitive cells in your eyes to collect images and transmit them to your brain. You have muscles that allow you to move around. But all of these are actually tiny little cells that are attached to each other or next to each other and collaborate with one another to make a human being. So if we zoom in and we look at one of those cells, they all have something in common. Imagine it like a basketball, right? So a cell has an outer membrane, and then inside the basketball, it has, imagine like a golf ball inside. That little golf ball that's floating around inside is called the nucleus. So you have the cytoplasm, the whole cell, and then that little golf ball, which is the nucleus. But you could think about this as let's say a factory. The cell is supposed to do one thing all day long. It's either muscle fiber, or it's making light-sensitive proteins, or it's creating acid in your stomach, or whatever. And the golf ball is the manager's office, and the rest of it is the shop floor. And the manager has something in his office called DNA, and DNA is the instructions for making everything in any cell in your body, but the manager knows which part of that DNA applies just to that cell. So he knows what that cell is supposed to be doing, and he just makes copies of the parts of the DNA that are important for the cell, and he just sends them out all day long. And the cell, all the machinists that are on the shop floor inside the cell, just go ahead and make whatever the manager says. And that DNA, though, is the critical piece. It is actually software. It is a recipe for everything that the cell does. It is instructions coded in what are called nucleotides. Now, you know the computer on your desk or in your pocket is coded in zeros and ones. Frequently you program in higher level languages, but they all translate to zeros and ones because that's how digital computers work. A circuit is either on or a circuit is off. And if you arrange these circuits in the correct way, you make a computer processor, and those on and off signals can translate to all different types of instructions that are important to digital computers. Now, on the other hand, cells work in nucleotides, which are either a nucleotide that's symbolized by A, C, T, or G. So there's 4 different symbols that are in the instructions for these tiny little computers in your body. That is what makes up DNA. The order of those ACTGs is what determines what the instructions are. It determines what the cell makes. So the zeros and ones are arranged in a certain order for instructions in your computer, but the ACTGs are the instructions of the cell. And there's so many parallels between the cell and your digital computer and the software that you're doing. So think of that DNA in the cell as being the operating system of the cell. It's like the iOS on your phone or the Microsoft Windows on your personal computer or whatever. And the thing about humans is that we can be born with bugs. In other words, sometimes you don't get a perfect copy of DNA. As a matter of fact, there's no such thing as a perfect copy. There's a lot of different types of DNA that you can get, say different expression levels of these instructions. That's why you look around the room and we don't all look the same. It's just teeny changes in our DNA. We're all basically the same. No matter who you're looking at across the room, that person is 99.99999% the same as you. And that is because their DNA is that similar. So the small changes can make big changes on our exterior, but we're basically all the same inside. So, but you can get a bug. You can get a little broken piece of DNA. And if you inherit a broken piece of DNA from both of your parents, you can actually be missing some instruction that some cell in your body needs. Like, for instance, it could be missing something that is an enzyme in your stomach that helps you to digest milk, and you could be lactose intolerant. Or, it could be something, some other type of digestive problem. It could also be something more serious, like a metabolic disorder, something you're not making in your blood, like hemophilia. And anyway, hopefully none of you have any of those problems, but it turns out that 1 in 10 people on the earth has at least one what's called monogenic disease, at least one broken gene. And that can range from inconvenient to actually quite serious. Well, those bugs can now be corrected. We can reprogram those bugs. If the order of the ACTGs isn't right, we can chop that out and put in something new that is correct. And that's the future of medicine. In other words, instead of giving you drugs that sort of soak your cells and sort of nudge them to do the right thing, we can now go into the actual base operating system of your cells. We can reprogram them, and we can change all of the things that drive the behavior of that cell. It's incredibly powerful, and here's how we get into the cell and make those changes. We do it with viruses. That's right, viruses, common viruses. Scientists believe that viruses have been on the planet for about 1.5 billion years, and what they do is they carry little pieces of ACTGs, little pieces of code, kind of code that you write, into the cell, drop them in there, and by dropping in the viral DNA, they hijack your cells to do something bad. So what kind of things would that be? Well, a cold will start attacking cells and give you the symptoms of a cold. The flu will do the same thing. You have an immune system that fights these things, and usually your immune system can fight off things. But there are some viruses that your body can't fight. As a matter of fact, right now, like I said, we're facing COVID, and there are some people that can't fight off that virus. But in any case, the point is that the virus, the way it works is it brings in these little snippets of code, deposits them in cells, and that's how it takes over the cells. Well, it turns out now scientists have the capability of cracking open the most deadly viruses on the planet. In fact, we've already cracked open COVID. We know exactly what it looks like inside. We haven't solved that problem yet, but we know exactly what the ACTGs are that it's bringing into your body, and that's going to help us to find a solution more quickly. So once we crack open a virus, we can scoop out its little code segment. We can go ahead and throw that code segment away, and we can replace it with whatever code segment we want. So we're using viruses as updates. We're converting deadly viruses into helpful updates that, instead of making you sick, make you healthier. Can you believe that? It's incredible. It's incredibly powerful. It's working right now. There is a cure for blindness that uses this technology, 2 cures for cancer, a cure for bubble boy disease. Have you ever heard of that, where people are born without immune systems? That's now curable. There's a cure for spinal muscular atrophy. People that are born with that one gene broken die by age 4. It's terrible. But now we have the ability to take these deadly viruses and repurpose them as updates, crack them open, scoop out their code and throw it away. What's left? It's like an empty diskette, right? We can put software on that and then we can deliver that into your body. Those diskettes go into your cells and change all the code there. So that's the remarkable world of what we call gene and cell therapy. That's what my company does, American Gene Technologies. And actually there are many companies in this field. And the future just looks amazing. There's 7,000 monogenic diseases that are likely to be cured. We're actually using lentiviruses. We're using a viral solution to cure HIV. I don't know if you've ever heard of HIV, but 1 million people have it in the United States. And what we can do is make them permanently immune to HIV, so they're just normal people. So it's very exciting stuff. It's very powerful stuff. You are beginning a career in coding that could even go into that if you choose. And like I said, one of you out there might actually cure COVID. But if that's cured before you get into college or whatever, well, no problem, because there's plenty more things to cure. You'll be curing cancers. You'll be curing all sorts of viral diseases. You'll cure the next pandemic. All right. Well, thanks for listening and good luck with your coding.